In this video, we're going to learn about how to add vectors. We'll start with some basics about adding vectors, then we'll move into adding parallel and perpendicular vectors, which are the easiest ones to add, and then we'll talk about in general how to add any two vectors. For starters, you'll see that I have three vectors up on my screen here. Could I add the pink and blue vectors together? If you answered no, you're correct. To add any vectors together, they must have the same units. What about the pink and the green vectors? Could I add those together by saying 5 meters plus 3 meters equals 8 meters? Once again, the answer is no, because vectors have direction. So when I'm adding vectors, I must pay attention to their direction in addition to their magnitude. One last fact about adding vectors is that when I add two vectors together, the result is called the resultant vector. I'll use that term multiple times in this video. Let's move on to adding some vectors, starting with adding parallel vectors. You'll see I have multiple vectors here. If two vectors point in the exact same direction, adding them is simple because all you need to do is add their magnitudes. For example, if I wanted to add the green and the blue vector, the total would be 7 units. That's the resultant vector. Similarly, if I wanted to add the black and the pink vectors, the total would also be 7 units. So the resultant vector would be 7 units downward. But if I want to add two vectors that are in opposite directions, such as the green and the black vectors, then I have to pay attention to direction. Adding two vectors that are in exact opposite directions is the same as subtracting their magnitudes. So the resultant vector of the green plus the black vector would be 2 units upward. Let's look at adding vectors if they're perpendicular. Here we get a little more complicated. Now we can't just add or subtract magnitudes. When things are perpendicular or neither parallel or perpendicular, we're going to draw pictures of these vectors. So you'll see that I already have the vectors drawn. I'm going to start off by adding together the pink and the green vector. What I need to do when I'm drawing a diagram for this is I need to place the vectors tip to tail. In other words, I'm going to move my green vector so that its tip is located at the tail of the pink vector. I could have also moved my green vector so that its tail is at the tip of this pink vector. I'd get the exact same thing. Then I will draw my resultant vector by starting off at the tail that's all by itself. In this case, that's the tail of the pink vector, and drawing an arrow toward the tip of the green vector. That would be my resultant vector there. To find its magnitude, I could use the Pythagorean theorem. And to find its direction, I always find the angle that's at the tail of my resultant. So that's the angle that I've marked with theta in the diagram. Let's look at that again with the other two vectors on my screen, the blue and the yellow. I could move the blue vector so that its tip matches the tail of the yellow, or I could move it so that its tail matches the tip of the yellow. Either is perfectly acceptable. Then, as I'm drawing my resultant, I start off at the tail that's all by itself, and I end up at the tip that's all by itself. Again, I would use Pythagorean theorem to get the length of that vector, and I would use trig to find the angle, which is the angle at the tail end of my vector. So we're going to try it out. We're going to try a couple of examples. This first example combines concepts of one-dimensional motion with what we're now learning with vectors. We have a hiker who's walking around 3 kilometers north and 4 kilometers west, all in 1 hour and 40 minutes. And we're asked to do two things: calculate his average speed and calculate his average velocity. Well, if you think back to our chapter on one-dimensional motion, you'll remember that average speed is distance over time. So part A doesn't require any vectors at all. The total distance my hiker travels is 7 kilometers. And then I have to put the denominator in hours because it wants the speed in kilometers per hour. 1 hour and 40 minutes is 1 hour and then 2/3 of an hour. That's 40 minutes. If I do 40 over 60, I can reduce that to 2/3. I'll write that in my equation as 1.67 hours. Dividing 7 by 1.67 gives me an average velocity of 4.19 kilometers per hour. And I apologize, that's average speed, not average velocity. Then I get to part B. Part B wants to know the average velocity. Here's where the vectors matter. So I'll start off by drawing a picture. It says that he walks 3 kilometers north and then 4 kilometers west. Your picture doesn't have to be perfect, but it helps if you have that 4 kilometer vector being a bit longer than the 3 kilometer vector. So then my resultant starts out at this tail that's all by itself and goes to this tip that's all by itself. Now the really nice thing is that this is a common triangle, 3, 4, 5. We're used to that number. So I can tell that his displacement is 5 kilometers. That's the magnitude at least. So if I were calculating the magnitude of the average velocity, I could do 5 kilometers divided by, once again, 1.67 hours. And I would find that the value is 2.99 kilometers per hour. But wait, we're trying to find average velocity, and average velocity is a vector. That means I must know a direction. So this is not a complete answer yet. I need to find the angle, and again, it's always the angle at the base or the tail end of your vector. So it's the angle that I've marked with theta in my diagram. While I could use any trig function to solve for that, since I know all 3 parts of the triangle, I prefer using the tangent just because that uses 2 values we were given in the problem rather than the hypotenuse, which is something we calculated. So if I'm using the tangent of theta, that would be the tangent of theta is 4 divided by 3, or the inverse tangent of 4 over 3 equals theta. When I do that, I find that my angle is equal to 36.9 degrees. And remember that we have to talk about where that angle is located. I can't just say 36.9 degrees and be done with it. So in this case, I'm going to use the directional and say that that's 36.9 degrees west of north. Again, that angle would touch the north axis if I were to draw a little XY axis here. So it touches north, so north is my second direction, and I had to go west of that. Just as we talked about in class, this is not the only way to talk about what that angle is. Let's move on and try another one. Actually, as a matter of fact, I want you to try this one. This is part of your homework for tonight. Try this problem and bring it with you to class tomorrow, and we'll go over it. One thing to point out about this problem is that it's asking what his third displacement is so that he gets back where he starts. So when you draw your picture, it's not going to look the same as if we were just adding the 2 vectors together. Instead, we'd have the 8 meters west and then 13 meters north, and then opposite the direction what our normal resultant would be, that would be the third displacement. And that value, that blue one, is what you're looking for. Okay, so what happens if we have vectors that aren't parallel or perpendicular to each other? just like these two vectors right here. Well, there's two methods for adding vectors technically. One's called the graphical method, and one is just kind of with numbers. So let's look at the graphical method first. What I've done is I've put these two vectors on a XY axis with evenly spaced markings, and you can see that these two vectors have been placed tip to tail. So my resultant would start out at the tail that's all by itself, which is at the origin, and would go toward that tip that's all by itself. Based on the fact that it's on this nice XY axis, I could figure out its X and Y components. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 would be its X component. And the Y component is pretty easy to see that it's 2. We've already talked about once you get X and Y components, how to find the total. So it's pretty easy when you're doing it the graphical method, but as we discussed in class, not very convenient, because that means that you'd have to do every single problem with graph paper, a ruler, and a protractor, and be very precise in your drawings. So let's talk about how to do it without graph paper. Let's talk about how to do it in the normal, non-graphical method. I've come up with 6 steps here. We're going to follow along those 6 steps. I encourage you to pause the video right now and take some time to write down these 6 steps. I'll make sure that they all get on one screen. Actually, I can't fit them all on one screen, so I'll do this. I'll scroll down in a couple of seconds, so when you unpause the video, you'll be able to see number 6. Now that you've seen the 6 steps, let's look at exactly how to use them. Let's apply them to a problem. In this example, we're talking about a plane that's flying to 3 different locations. It goes from base camp to Lake A, and then Lake A to Lake B, and we're trying to find the distance and direction from the base camp to Lake B. We start off with the very first step, which is to draw a diagram. So, as I'm drawing my diagram, it's not important that I have a nice pretty picture for base camp or Lake A or Lake B. It's much more important that I actually have the vectors drawn properly in there. So, I'll start off, and it says that I'm going 280 kilometers at a direction of 20 degrees north of east. Sometimes it's helpful to start with a little XY axis to help you interpret what 20 degrees north of east really means. 20 degrees north of east means that I start off going east and then 20 degrees north of that. So it looks something like that. That is 280 kilometers. And I'm going to mark the 20 degrees in there as well. Next, it says that the plane goes 190 kilometers at 30 degrees west of north. Again, it can be helpful to draw a little XY axis. And we're going 30 degrees west of north. That means I start off north and I go 30 degrees west of there. My vector looks something like that. 190 kilometers. So those are the 2 vectors I'm trying to add together. The resultant would start at the exact same place that we started the motion, so at the tail of the 280 kilometer vector, and would go toward Lake B. So this is my resultant vector. I'll just call it R for now. As you'll notice, it is helpful to name your vectors with letters. So I'm just going to call the first one, well, since it was going to Lake A, let's just call it A. And the second one, since it was going to Lake B, I'm going to call that one B. You'll also find as you do these problems that it is much more helpful to you to draw bigger diagrams. Now I know that means that you're wasting a little bit more paper, but trust me, it'll be helpful for the physics. Our step 2 is to split each vector into components, and don't forget negative signs if they're necessary. To split each vector into components, it's often helpful to actually draw the vector just by itself. So this would be vector A. When I do that, I can then draw its x component and its y component. This would be A sub x. This would be A sub y. Pause the video and find those two components. It's good practice for you. Hopefully you found that the x component of this vector is 263 kilometers, and the y component of this vector is 95.8 kilometers. To find those, I used sine and cosine. So for the x component, I did the hypotenuse, which is 280 kilometers, times the cosine of 20 degrees. For the y component, I did 280 kilometers times the sine of 20 degrees. Go ahead and do the same thing for vector b. Vector b is the one that looks something like that, which means its components would look like this. Not a perfect drawing, but you get the idea. Pause the video once again and find those x and y components. Hopefully, you found that the x component of b is equal to negative 95.0 kilometers. And the y component of this vector is equal to 165 kilometers. That x component is negative because it's pointed toward the left. That's what drawing this extra picture can help with, is remembering when to put in positive and negative signs. So our next step in our process is to add the x components together to find the resultant x component, and then add the y components together to find the resultant y component. When you do that, you find that the resultant x component is equal to 168 kilometers, and the resultant y component is equal to 261 kilometers. Our next step then is to draw those two components, putting them tip to tail. Here's what that means. I'll start out with the 168 and then 261. And then I can tell that my total resultant would look something like that. Now, if I were to compare this diagram to my previous one, if I had similar scales, I would find that those two resultants look pretty similar to each other. Now again, my scales are not perfect here, so they're not exactly the same, but they're at least in similar directions, and that's always a good sign. So this is 168 kilometers. This is 261 kilometers. And right down here would be the angle that we would be looking for. So, just as step 5 says, use the Pythagorean theorem to find the magnitude of that resultant. And then in step 6, you're finding the angle of the resultant using trig. Pause the video and do that right now. Hopefully you found that our resultant, in other words, the distance and direction from the base camp to Lake B, is 310 kilometers at an angle of 57 degrees north of east. Or you could have said 57 degrees ISP. You could have also said 23 degrees east of north, 57 degrees above the positive x-axis, or 23 degrees to the right of the positive y-axis. One more problem for you to do here. This is another one I want you to do on your own and bring to class with you tomorrow. It's good practice to try these on your own and see how much you understand them.